Hey, everybody. Welcome back. Everything is a spring. I'm here with Derek. Let's jump into today's episode, also about suspension bridges. But first, let's get into the preload. Derek, how are you doing?
I'm doing good, man. How are you doing?
Oh, I'm doing good. It's a beautiful day today. It's
For real.
November 18th.
Was it like 70
And
over where you are now?
it's 77 degrees.
Yeah, we're looking at a cool like 73 in the city, and it feels like spring, man.
Dude, it feels so nice outside. I was actually earlier today. I was at the Sugarcane Festival in George L. Smith State Park, which was super fun.
That sounds cool.
Uh, it was, yeah. So like they grow sugar cane down there, and they were like, this is how syrup used to be made, and so they've got like this like contraption that sits on like four wooden posts, and there's this log. Basically, it's like a 12-foot log that comes out of it. And basically, people like reach up and they grab onto the log and they walk it around in a big circle. And that turns like these grinding wheels. And so then somebody else feeds sugarcane into it and it crushes the juice out into a barrel.
What in the world?
And then they go and they boil that to concentrate it into syrup. And that's how syrup was made.
Dude, I swear where you live is you're just actually playing through Stardew Valley, because that's the Sugarcane Festival. We all just heave around this big human-powered wheel and make syrup.
Make syrup.
That
It
does
was
sound pretty
to see.
cool. That's some cool
was-
fall activity.
Yeah, it was neat. And then there was like some vendors and stuff, and that was kind of fun. But yeah, like the big thing was like the sugar cane, and that was pretty cool.
Right on, man.
What about you? What you been up to?
Oh man, this week's been busy. I've been like really busy at work, but I have some cool stuff coming up tomorrow. Speaking of podcasts, one of my favorite podcasts, that besides this one, obviously, is one, Well, There's Your Problem. Two, Welcome to Night Vale, as you know, has been like, I think that was the first podcast I really got into. And sure enough, we got a show, like a live show, and me and one of my friends are going to tomorrow. So I'm really hyped to actually see them live. I've seen them live once, and they put on a heck of it's more like a whole stage production than just a podcast reading at this point. Like there's music and special guests and stuff. So
That's awesome.
It's exciting to like I have to edit this tonight, but actually get to enjoy like from a distance tomorrow. So I'm looking forward to that.
That'll be awesome. Awesome. That sounds awesome.
And
So
we got some
Welcome
more
to
merch.
Night Vale?
Yeah, Welcome to Night Vale.
We have more merch. What?
Well, not officially, but I was telling you a little bit before we started recording, I got Jim some Christmas presents. Everything's a spring themed, right? And I did get myself a Christmas present too, because like Jim loves hats, right? He uses hats all the time. I don't usually wear hats, so I got myself a hoodie.
Nice. Oh, that's awesome.
I was like, I'm gonna get the Chef's Kiss hoodie. Like, oh, it's the nice fabric and it's Nike, got the logo on it.
Oh, absolutely. Awesome.
Yeah.
Oh, man, I guess, let me see. I'm trying to think about like, what do we have to discuss? Because we kind of accidentally discussed all of our stuff before we started recording.
Yeah, it was mostly just me asking how business was and just catching up,
That's true. Well, we won't go into business too badly. I think we've got a fairly beefy episode, so I guess we can go ahead and jump into it.
Man, I'm telling you what, I know my excitement was shown last week. As I was editing, I was like, I need to tone it back a bit, because bridges are cool, man.
Bridges are cool. Bridges are very fun. So yeah, I guess I'll just go ahead and ask my question. Derek, how do you feel about clowns?
How do I feel about clowns? Like the circus clowns?
Yeah, like circus clowns.
Oh, gosh. I'm not like afraid of clowns, right? I might be a clown in hindsight, even though I don't look like one, but I don't know. I'm indifferent about clowns. I don't dislike them. I don't seek them out.
That's fair. I feel like there's been this kind of interesting cultural evolution of clowns, right? Because apparently, like back in the day, like clowns were like really popular, right?
I
Like
could
that
see
was like
that.
a whole thing, right? And then somewhere along the lines, clowns kind of became like this super creepy thing. Where do you think that started from? Like, where do you think that stemmed from?
My guess would be film, right? Like, I know we have like the It movie in this generation, but there was a couple of like, I don't know if they're called indie horror films, where you know, in the 70s, 80s, it was just like, oh, you have this clown like outside of your window, and it like, I guess became this kind of like taboo media. Because like clowns usually are supposed to be like, you know, they go to a kid's birthday party. It's not this scary thing. But I'm guessing there's something I don't know.
Well, I actually just Googled it because I was curious.
Is this like a culture shift?
I mean, I guess it must have been, right? So, because like there's this guy named Bozo the Clown who was really popular in the 60s.
Yeah.
And there was like a 10-year wait for his tickets, like to go to his show.
People were like, yeah, I remember hearing about Bozo the Clown. Like he was the clown, like that got marketed.
Ah, okay. So here's what happened. So there's a serial killer named John Wayne Gacy, and he masqueraded part-time as a clown named Pogo in the 70s. And so then when it came out that he was a serial killer, he people were like they branded him as the killer clown.
Oh, I could see that. It's like all over the papers.
Yeah, that's where it starts. So,
but he didn't kill anyone as a clown, right?
No.
He just happened to be a clown on the side.
So I think he was a clown on the side, and then part-time clown, part-time killer. Ruined
clowns for everyone. Well, I guess he jump-started the It killer franchise, I guess.
I think so. Like I would imagine, yeah. So I'm looking at this is an article from ABC News. So he kind of begins the killer clown stereotype, and that's where It comes from. So apparently I guess It is like not really a clown, but I don't really know. It
looks close enough to a clown for like the imagery, right?
Right, but isn't Pennywise like supposed to be like a demon or something?
I think so. He's like possessed. I'll be honest. Half the time when I watch those movies, I'm half paying attention because I'm waiting for jump scare.
That's fair. That's honestly fair.
Interesting. A fun aside about clowns and their origins.
Yeah.
Or the fear of clowns.
The fear of clowns. Anyway, yeah, that's besides the point, really, to this episode. So we'll close that tab out. But let me set the stage for you. So the year is 1845 in Yarmouth, England. Which Yarmouth is on the... it's by Norwich. It's basically on the very easternmost point of the island of Britain, facing the Netherlands and France. And it's kind of like northeast of London. But it's basically like this big kind of like inland bay that I guess would be very, very good for keeping ships and stuff, because you don't have to worry about the ravages of the ocean destroying your vessels in port. So,
oh, that's nice.
Yeah, so that's very good. So it seems to be it's a very important port city. Is really all that's relevant there. But anyway, so that is the year is 1845, and let's say this is obviously before our friend whatever his name is, the clown, who turned clowns into evil monsters.
So people were hyped for clowns. It's clown time.
People were hyped for clowns. And also, I think the use of the term clown was a little bit different. But basically, there's this guy named Arthur Nelson, and he's a clown. And the Royal Circus was in Great Yarmouth, and they advertised that Arthur Nelson was going to sail up the river in a wash tub pulled by 4 geese.
All right, there's a lot to unpack there.
Hit me with it. What are your thoughts?
Oh God!
Would you gather to the river to watch a man in a bathtub? You'd buy those tickets. Oh man,
it's 18. What else is there to do? I'm buying those tickets. You know, like I could see. All right, I see the lure. You're not. You gotta remember, not afraid of clowns. So this is probably the funniest thing you've ever seen. 3 parts to that. Going up river in a bathtub, pulled by geese. Why?
Well, I mean, honestly, I'd pay tickets now to see it.
If someone wants to. Was it like is geese a term for something I don't know? Or are we talking about the burb?
No, this is 4 real geese. So I'm looking at like the newspaper clipping from the time. And it says, Mr. Nelson will sail on the River Bure, starting from Yarmouth Bridge to, I think it's, I can't read that part, but there's some gardens, at 5 o'clock on the above day, which is May 2nd, drawn in a washing tub by 4 real geese. That's the title of the ad.
I love how they have to specify real geese, so it's not like he's just some folks swimming in a goose costume.
Right, absolutely.
What in the...
So,
oh, Jesus Christ.
yeah, I mean, and it's basically what it is it's a publicity stunt, right?
No, for sure.
So they're basically trying to like drum up business for the rest of the circus by having this public display.
Oh, this isn't an advertisement for Big Goose?
No, Big Goose does not have any relevance, I guess, to what they're doing. There are potentially some bathtub sponsors.
Ooh, I could see that.
As part of it.
It can survive across the river. It'll survive your busy lifestyle. Come out of the mines and jump into our tub.
Exactly. So, yeah, whatever wash tub he's using, we got to get that. It's
That's
stable enough to go up river.
It floats. It's good around water. What else could you want?
What else could you want out of a tub? So
that's wild. So this guy, the publicity stunt is a clown getting pulled in a bathtub powered by geese, and this is an engineering podcast. Go on.
Oh, absolutely. So, of course, he's not actually being drawn by 4 geese, which is kind of the tragedy of this whole thing, really. So there's actually a rowboat and a rope underneath the water that goes to this rowboat that's pulling him.
Oh, false advertisement.
Yeah, I'm
powered
a little bit
by goose.
Exactly. So I'm like, that's kind of unfortunate. I really wish they had gotten how many geese does it take to pull a clown in a bathtub upriver?
I'm sure we can calculate goose power compared to horsepower easily.
I think so, especially like in water.
How angry are the geese is the common factor,
That's true, because there are a few things that man should fear more than an angry goose. As we were saying, like clowns, mad fire at the time.
Hot flames.
Hot flames. A man being drawn upriver by 4 geese.
That's the show of the year.
That's the show of the year.
Everyone's excited.
It is. And so there's a large crowd of people who gather on the Yarmouth Suspension Bridge.
Here we go.
Here we go. On May the 2nd to go view this.
May the 2nd, 1845?
1845.
Oh gosh, listen, bridges.
And basically several thousand people are viewing the clown from the riverbanks, and about 300 people are on the southern footway of the bridge.
That's a lot of folks.
It is a lot of folks, and they're all concentrated on one side of the bridge.
Oh.
So, yes. So, let me tell you a little bit about this bridge.
Okay.
The Yarmouth Bridge...
Paint the picture.
...was made in, I think the actual... Yeah, so the bridge opens for public use on April 23rd, 1829. And originally, it is 2 footpaths, so basically a sidewalk on either side of a carriageway. And it is originally a 14-foot wide deck. And then it is 92 feet between the iron towers that support the bridge.
All right. It's not too big of a bridge.
It's not horribly large, but it's still a pretty good size. I mean, I guess. So like 92 feet, like that's pretty long, right?
Yeah. That's like, what, 30 freedom units?
Yeah, I guess it'd be 30 yards. Yeah. Feet is freedom units.
Oh, yeah. That's advanced football freedom units. There you go.
Football freedom. Yeah, yards is advanced freedom units. Absolutely. So 100 yards. Is a football field's 100 yards, right?
Yeah, and it's weird because, like, I played football. I played soccer, right? But, on cheap football field turf. So it's like, that's my measure of distance. It's like 100 yards. I know what that is. I know how to split that into a third. I can throw that. Easy.
Yeah. So this is, it's a substantial bridge, but it's not like ungodly
Yeah.
in its size, right? It's not enormous,
But it's
it's
1845. Like, come on now. It's a nice
yeah,
gallivant.
and it was built in 1829, right? So even a little bit earlier when it was made. So the bridge is supported by suspension chains, as we've talked about, at both edges of the deck. So there's basically, obviously, two sides of the bridge. And each of these chains is formed from two sets of 7/8 thick eye bars, which are basically like, they're just a special type of chain, basically. But basically they are, it's a rod with two eyelets at either side. So it looks kind of like a wishbone, right? So if you take like a bone and then drill a hole on either side, like that would kind
And
of
then
be
you
what you're
connect
looking
them
at.
like that. Just multiple.
And then you connect it. Yeah, and then they're like looped into each other.
So it's less flexible than when I think of a chain today. Like these
Correct.
are pretty
So,
rigid structures.
yeah, so it's basically, it's not a standard like chain link chain that we would think of today. It's really, I guess it would look more like a bunch of turnbuckles all kind of hooked together.
Right on.
If that makes sense.
Like they can articulate off each other, but not by much.
Yeah, well, I mean, they can articulate off each other pretty well, but like the chains are basically, each link of the chain is like a lot longer than we would normally think of a chain would be, if that makes sense. But anyway, and all these eye bars are made by a local blacksmith. And so then as time goes on, they're like, oh, we need this bridge to be bigger. And so they decide to widen the bridge, which is always a good decision.
Yeah, just
to widen.
Just slap some more onto it.
Yeah, that won't hurt anything.
No, just slap some more onto the original structure that if someone did math for, it'll be fine.
It'll be fine. And originally, the original design for the bridge actually only had it as a 63-foot span.
Oh, so they're already going past spec on V1.
They're already going past spec. And then once they, in 1832, they made it wider, right? And so they widened it by 2 feet on either side. So now it is, about 16, 17 feet wide.
Okay.
And there is now room for 2 walkways and a carriageway, or 2 carriageways, excuse me. So it's basically a 2-lane road and basically a sidewalk either side.
Wow, 1800s and they had freaking sidewalks. Crazy.
And then in addition, they basically put the railings all the way out to the edges of the deck in order to basically provide a little bit more room for the walking path. And that increases the overall width to 19 feet and 10 inches, which, if we do the math, is a full 5 feet pretty much wider than it was originally intended to be. So keep that in mind because that'll come into a factor. Basically, that adds about 2 long tons of weight to the bridge.
That's a lot for a bridge that's already over-specified.
Yes, so that adds about 6,000 pounds to the bridge compared to the original deck, which is the original deck in total is about 40,000 pounds. So you're adding an extra 6,000 pounds to the bridge.
This is fine.
Which I'm sure is fine.
That's a lot of weight, but bridge, go Burr.
Yeah, so let me continue talking about this bridge. So basically, the suspension bridge, the main element are these 2. Obviously, each side has a chain, and then each of those sides is actually 2 chains. So it's 2 sets of these eye bars that I talked about, and then there are actually vertical iron rods, just solid iron rods that come down from the suspension chain and then attach to the deck of the bridge. And that's what actually supports the weight of the bridge along its span.
Gotcha. And are the chains connected to these iron rods, or is that just?
They are.
Okay.
Yeah.
Gotcha.
So the chains are basically the iron rod is hooked to the chain and then it's hooked to the walkway, and that's what supports the weight of the bridge.
Cool.
So then, Yeah, so then the bridge reopens in 1844 with a widened causeway, and the railings moved and everything.
Big old
And
thick
that
bridge now.
big old Tickums Bridge.
Thickums Bridge.
So that brings us back to the 2nd of May, 1845, as we see, Mr. Nelson in a wash tub drawn by 4 geese floating upstream underneath the bridge. So as all these people are on the bridge, it's about 5:40 p.m., and there's 300 people on one side of the bridge gathered as close to the railing as they can.
Oh, now that I've visualized the bridge, I see where this is going. Holy cow.
Oh, yes. So around 5:40 p.m., one of the eye bars in the suspension chain fails. And somebody in the crowd witnesses this. It's noted that somebody sees this happen.
They just saw it break?
Yeah. And then nobody does anything.
Oh, that's strange. Well, anyway, where's that clown?
Right, because there's the second chain, right? So there's each side of the bridge has 2 chains. So if we remember from last week, we talked about the Broughton suspension bridge failure. It only had 1 chain and 1 bolt fastening the suspension components of the bridge to the ground, right? So that was kind of like, oh, maybe we should double up. So in this case, they did. They had basically
redundancy.
A redundant chain, absolutely. But nobody evacuates the bridge. Basically, everyone's like, oh, I guess it's fine. The bridge didn't fall down, so we're fine.
I love how that's what it takes. It's just like, wow, something just fell off the bridge. Anyway.
Yeah, it's just like, anyway, have a look at Mr. Nelson down in his wash tub drawn by 4 geese.
To be fair, that's a pretty reasonable distraction.
I will admit, that'd be pretty cool to see.
Because they got the best seat in the house for now.
They do, absolutely. And the real tragic... Well, we'll get into that.
The real tragedy.
So basically what happens is, for about 5 minutes, the entire weight of the bridge with all the people on it on the one side is held by the single chain remaining on that side of the bridge. And then it finally fails. And the south side of the deck falls into the river, and although the north end remains, suspended, basically. So you have the same tipping motion, and it just dumps people into the river. And it throws people like against that iron rods that are connecting. Yeah, so like it's just this mess. Like people are getting tangled in the remnants of the chain and the iron and everything.
Oh, so this is the environmental effects that you were talking about, and the environmental effect was the people?
I actually changed which topic we were going to cover today.
Oh,
so actually, the environmental effects will have to wait until next week.
Gotcha. That's crazy. All right, so you got 300 people on one side of the bridge getting, I'm talking, catapulted down into one, because bridges don't fail softly from what I've seen.
Yeah. Very suddenly, right? I mean, so it's the full weight of everything just falling, right? So it's just this sudden fall. And then, hold on, I'm getting a call real quick.
No, take your time. Oh, it's podcast time. Ooh, baby, podcast time. We're doing a little bit of a wait while Jim takes a bit of a phone call. Podcast time. Ooh, I'm talking podcast time. Ooh, podcast time. Ooh, podcast time. A little breaking podcast time is good. We're learning about bridges today. I'm talking about bridges today. 1845. But don't forget, it's podcast time. You gotta remember it is podcast time. Even when you're breaking. Oh, you know we're not faking. It's podcast time. Podcast time.
I saw you gooning over there. We're not cutting any of that.
Oh.
All right, and we're back. We are going to spring back into our episode right now. Okay, so basically, where were we? Basically, all these people are falling into the river. And now comes kind of the real tragedy, which is, you know who really likes clowns?
Children.
Yeah, children.
Oh.
Yeah. So basically, like the crowd is like 4 or 5 people deep, crowded up against the railing, and these kids are in the front.
Oh, they're like
And
climbing on the rail?
Yeah. So then, like, all the people who are behind them get shoved basically by gravity
Yeah.
into these kids.
Oh.
So everyone just gets like piled against the railing and then dumped into the river.
Oh, no.
Yeah, which is not good. Yeah, so a lot of kids end up drowning, which is really terrible. One of the notes here is that one child was saved from being swept away by her mother holding on to her clothes with her teeth.
Oh, a mother's strength. That's wild.
Yeah, so just like, just
you ain't going
nomming
nowhere.
on these clothes, which I think is just wild. I would love to see that.
The adrenaline to... God.
Yeah, like, that's a lot of teeth strength.
I mean,
like, what's
that's
that mouth
determination.
do?
Oh, God. Yeah, like, you got to think about the reflexes to reach out and chomp. And you only get
on
one
your
chomp.
child's clothes. I know, right? Like, I'm impressed by the reflexes and the hand-to-mouth coordination.
Oh, for real. That's what that mouth do.
That is what that mouth do. Dang. Like, wife of the year. Am I right, boy?
Oh, my goodness. A mother's love has no bounds.
Indeed. But, yeah, so, I mean, there are these, like, tales of incredible heroism. But it's still really bad. I mean, and the river is about 7 feet deep at this point, and it's a fairly quick stream, I guess, at this juncture. Like, it's a fairly large river, so like the current is strong, and so there's boats that are scrambled to start rescuing people. The wounded and dead are taken to nearby houses and pubs to basically be taken care of. There's like a pretty good response, I guess, in terms of like the rescue effort. There are some people who are actually trapped in the wreckage of the bridge, but are either are able. Some are able to be rescued, some are not.
That's brutal. Like, you're getting folks crushed on the top, hitting the chains on the way down, and then you better be able to swim because you're saying that there's a current to sweep you.
And in 1845, a lot of people did not know how to swim.
Yeah, it wasn't like a recreational thing, right? It was
not a recreational thing, absolutely. So that is really unfortunate. 79 people were killed in the disaster. 59 of those people were children.
Oh, no.
Yeah, and most of those killed were under 13 years of age, which is really quite tragic.
This is supposed to be a good day.
I know, like,
you got
we had
this
the clown.
Headline. That would be the best. Can you imagine it's your birthday and you're like, I'm about to see the most odd thing I've ever heard in my 13 years.
You got this clown in a bathtub drawn by geese, and then you end up dead.
Dang, man. That's super sad. Like, I didn't even consider it's a kid's attraction. That's who goes to circuses.
Absolutely. So
that's a lot of dead, man.
Yeah, it's really sad. And so the next day they have a coroner's inquest, and we've actually talked a little bit about these on the show before.
You got to do your record keeping, record
keeping. So the inquest is basically is done, and as part of this, because it is, there's actually this group called the Institution of Civil Engineers at this point in time in Britain. And the British government commissions this guy named James Walker.
Hey, that's you.
To basically go and, let's say, like, investigate, be part of this inquisition not inquisition.
Cool. That's a totally different civil
that's a whole different thing.
endeavor. Holy cow.
Nobody expects the Spanish Inquisition.
Oh, God. Solid. So it's interesting that the municipal government at the time was smart enough to ask the engineers for help.
So like this is, so again, we're kind of in the middle of the Industrial Revolution. And this is at the point where they're starting to become these like societies of engineers and stuff like this,
Yeah.
where there is a little bit more, there's a little bit more of a community within the bridge building space and like stuff like this. And people are starting to make names for themselves as bridge designers and stuff. And we're starting to see like the very foundations of regulation really being laid through these types of tragedies.
Yeah, and honestly, standardization, because you have these groups of, like, I guess not foremen, but, engineers of the time actually having an information share. So maybe one bridge across town is maybe managed by a different group, but you're starting to learn lessons together.
Absolutely. And we'll get into like the fundamental like outcomes of this beyond the human loss in a few minutes. But basically, Mr. Walker, he finds that the original specification for the bridge had called for, quote, high quality iron to be used for the eye bars that made up the suspension chain. But he hadn't actually like specified any sort of like testing or actual like
like what's
specific requirements,
the
like what
tensile limits of it. They just said high quality, the good stuff.
Yeah, like what's high quality iron, and how do you test if iron is of high quality, right? So like
that is oddly ambiguous and likely intentionally ambiguous.
Well, it's extremely vague. I think I don't know, right? Like, so it's hard to say.
I know what this is. Yeah, high quality iron down at Frank's High Quality Iron and Dispensary. You gotta listen, boys. You ain't getting iron unless it's from Frank.
It's just an ad.
It sounds like, what is high quality iron? That's so vague, even for the 1800s.
Yeah. So, and again, like, because remember, the bridge was actually built in 1828, right? So the bridge has been around for like 20 years at the point of failure by the time it fails.
That's a lot of weathering.
And it's been altered, yeah. So there's a lot of stuff that's been happening. And we'll actually talk a little bit about fracture mechanics today here in a few minutes. So basically what they find is that they failed to say like what qualifies as high quality iron, like what's the test for that.
Right.
And then he finds also that the failure occurred in both of the eye bars in a joint within the eye bars. So the eye bars were basically forged from three pieces. So there was basically the rings that made the eyes, and then the rod that connected them.
Are these welded together?
And these are forge welded, scarf jointed together. So when you're forge welding, generally what you do is you create what's called a scarf joint, which is you create a thick section of metal that you can kind of, if you take your hand and you cup it, and then you take your other hand and you cup it as well, and then put your hands over top of each other, you'll kind of see you've got like this thick section of your hands relative to your arms. And so then what you do to forge weld those is you heat them up to about 2,000 degrees Fahrenheit, and then you hammer them together. And what that does is basically it flattens out that thick section and then brings it into the same dimension as the rest of the material. And at the same time, that creates a molecular bond between the iron molecules between the where that scarf joint was.
So like it's thicker metal, but it ends up being the same diameter across the whole thing, but it's denser at the point of the joint?
Not exactly. So the only reason you start with that thicker material is because as part of the process for forge welding, you have to hammer it down. So if you started with two pieces of metal that were the same thickness as the rest of the stock, you would actually end up with a thin section where you welded it. Does that make sense?
Yeah,
because you have to forge it down.
But the density doesn't change.
The density doesn't change, right? So the forge weld actually, not molecular bond. It creates basically a continuous steel microstructure, right? So because when you look at steel at like a functional crystalline level, it creates like crystals basically. And the goal of welding is to make that crystalline structure homogeneous, basically. The problem with forge welding is that, especially in 1845, is that you're forge welding in coal, and you're forge welding, in this case, with material that may or may not be of high quality.
High quality in the biggest quotes.
Right, and like, what does that even mean? And so it's very common in forge welds, especially compared to like modern welding technology. It's very common to have inclusions or fractures or little pockets where there was a little bit of slag that basically the weld doesn't take. Because in order for a forge weld to be successful, it has to be very clean. Like the metal has to be very, very clean to each other. Because you want as little barrier for the iron microstructure to homogenize and kind of grow together and bond. And any contaminants can prevent that from happening. So contaminants can be anything from like a piece of sand or a piece of iron oxide or slag or whatever, right? So it's not uncommon for forge welds to have impurities or inclusions that prevent it from being a fully complete like weld, basically.
Interesting. So so this is where you get into your fractures. Like we're thinking of something that's supporting a huge amount of pressure all the time.
Yes, and these chains are supporting. Yeah, they're supporting this whole bridge, right?
So the chain itself failed. Like it just broke.
Yeah. So that the chain links broke. Yeah, they burst. And so the first one, the first rod, only covers like 5% of the total like surface area of like cross-sectional area of the rod eye. So like that first, like this is the other thing too, right? Is like this is a huge chain, right? And so it's got probably hundreds, if not thousands, of these links, you know, in the whole bridge, right?
And it's crazy that of all that, someone saw this happen, or at least by their own account.
Well, yeah, because like one of the chains falls, right? Before the bridge falls, right? One of the chains falls, and then the basically, quote unquote, the backup chain, the second chain on that side, fails 5 minutes later.
Do you think if all those folks weren't on one side of the bridge, it would have collapsed like it did? Do you think the backup would have held?
Well, so the thing is, right, because you have all those people on one side of the bridge, you're concentrating all of the stress of that dynamic load onto one set of chains. So basically what you have is the north side that did not collapse, the north side of the bridge, is under relatively light load. Whereas the south side chain is under an immense amount of loading, even beyond what it normally carries. And, you know, if those 300 people were dispersed evenly across the bridge, the other chain would have been carrying like half of that weight. And so I don't think you would have seen a failure. Or you may not have seen a failure. The first link to fail had not been properly welded, and the contact was only like 5% of the cross-sectional area. So only like 5% of that weld had actually succeeded.
High quality. Yeah. That's not something that's checked? Or is that something you can check?
So you can. It depends a little bit on what it is. So part of the forge welding process, right, is because you're forge welding the interior surface of the bar, it is more difficult to visually inspect. But you can usually see there will be like a line. Let me see if I can send you a picture.
Right. Like 5% is not a lot.
No, that's very small. You can see like there's a little line where that scarf was. And you can inspect that. I mean, and so you can visually inspect that and see if it's starting to pry loose. Because on bad welds, you'll be able to see that line and it'll kind of go into the material. Whereas on a good weld, you'll still be able to make out that transition, but you can't like get a pick into it or anything like that. Like,
it's really flat, very even, and it's not going to be something you can slip material through.
Correct.
easily.
Right. So that's the ideal weld. So then that first chain that failed, basically there was hardly any metal actually holding that chain link together. The second chain link only had, I think it's 30% of the weld is structurally sound.
And they can find this out after it fails?
You can. So basically, what happens is when you find the two ends of the rod, there is going to be a section of it that was actually sticking together, basically, is going to be deformed, whereas the parts of it that were not actually holding together are actually going to have like rust and stuff on them, and they'll
Oh,
look
because of the weathering.
old because of the weathering. Exactly. So this is actually also, and this is going to go into another tangent, but if you look at like cyclical loading failure, you can see the same thing. So when you have cyclic crack propagation failure, what'll basically happen is you'll have a site at one end of the piece of material that fails, where the crack begins to form. And over time, as it continues to wobble, that crack grows and grows and grows until eventually the remaining material can't handle the load and it fails all of a sudden. And what you'll be able to see is in that area where it was slowly cracking and the crack was widening, you'll be able to see corrosion and discoloration and all this happening because that is now exposed to the oxygen of the environment. And so when you look at these types of failures, it's very easy to see, especially ones that take a lot of time to happen. It's actually pretty easy to see like where the failure begins because it almost looks like a beach because you kind of have these arching striations that start showing up. Let me see if I can get a good picture to send over to you.
Yeah, I have to keep this in mind the next time I'm reading through like a NTSB like after report.
Yeah.
Like things to look for if you're not an engineer.
Yeah, so this is a bolt failure that I've just sent you. But you can kind of see there's like kind of this beachhead area, and then there's this final catastrophic failure that happens on the right-hand side of the bolt. There's an area marked C where it just finally goes, and that's a very brittle failure at that point. But anyway, so then while the bridge is held up by this single chain, that chain link that fails stretches like a full inch under the weight of the bridge. I mean, so it's carrying this huge amount of load that it stretches for a full inch before it finally fails, and then throws everybody into the water.
And like this guy named James Walker figures this out in 1845 by just rummaging through the wreckage and knowing what to look for.
Yeah, basically. I mean, well, so a lot of this, they didn't really know about like all the stuff about fatigue failure and cyclic crack propagation and all that stuff. They didn't understand that. Really, fracture failure and fracture mechanics is still actually a relatively new area of study in engineering. So the guy who I guess we would consider like the father of fracture mechanics, his name is A.A. Griffith, and he really was starting to develop this stuff like around a little bit after the First World War. Griffith was trying to figure out why the actual stress that is needed to break glass is so much lower than it theoretically should be. And basically what he came up with is that glass is actually full of tiny little bubbles. And so all those little bubbles create stress risers that we've talked about. And eventually, at a certain point, all those flaws will propagate and create a failure. And so he kind of started looking at why that happens and started mathematically developing formulas to express how those fracture, I guess, thresholds might be calculated and stuff. And he wasn't quite right. And there's another guy His name is Irwin, who kind of comes after Griffith and starts modifying some of it and gets a more accurate, specifically for like ductile materials, gets a more accurate model that we actually still use today.
Well, that's cool. And
Yeah,
I guess
so
like it kind of increases with the technology. Like once you can actually look at it, you can kind of confirm your theories, like with modern microscopy.
yes, yeah. So you can actually, yeah, and like so. There's, I mean, fracture mechanics are still a huge thing. So are you familiar with like the Liberty ships, Derek?
No, what's that?
Okay. So the Liberty ships is probably actually something we'll cover at a separate point in this episode. But basically, the Liberty, or not this episode, but later on in the podcast. So the Liberty ships were a class of ships that were built for the Second World War in America. And it was actually one of the first times that like industrial welding was used to create ships. And part of the problem is that we didn't really understand how fracture works. And so the ships weren't all built correctly to account for potential flaws in the material. And as a result, like you have boats, like these ships, these Liberty ships, that would actually just split in half, like quite literally split in half.
Like the superstructure would split in half?
Yeah, like the whole hull would just split in half.
Yeah, that'll do it.
So, and basically it's because, in a ship, you've got this cyclic loading, right? Because it's being
you're
loaded
going over
by the waves.
waves
You're going up and down on
the
waves.
motion of the ocean, if you will.
And what happens is if you have flaws in the material that create cracks and you don't design it around, basically fatigue failure mechanics, those cracks can propagate and lead to very rapid and sudden catastrophic failure in a brittle mode. So what you're seeing here, for the listener, there is an image of a ship that's basically split in half.
It's like comically split in half, like straight down the gullet.
It is. Yeah, and so
it doesn't look real.
It's kind of weird because like literally the prow and the stern of the ship are just pointed downwards.
It's a good thing this happened in shallow water instead of like on the sea, right?
Absolutely, but there are Liberty ships that broke apart on the sea.
Oh, and there's just no recovering that. Like you'd sink so quickly.
Absolutely, yeah, because literally like the whole structure of the ship cracked.
Just gone. Wow.
Just gone.
Yeah, I hope we do talk about boats one day.
Yeah, we will definitely talk about boats. Boats are another great engineering point. But yeah, so like that's a little bit about kind of fracture mechanics.
Like the history of how you find out these things is pretty cool. I'd like to hear more about that as we go on.
Yeah, and one of the other things that fracture mechanics talks about and dictates is like, what's the minimum and maximum. So let me go into this just a little bit more. What is the maximum crack size that a component can withstand before failure? And then how long does it take for cracks to grow? And what is the smallest crack that we can assume is present in the material because of manufacturing defects or manufacturing process, right?
Oh, so you kind of get before they were building things that like assume a perfect material because that's just how the math worked out. Now we're starting to actually factor in. Okay, there's what do you call it? Relevant tolerances. I don't know what it's called in your industry.
Well, so it'd be like in engineering, a lot of time it's called like safety factor.
Okay, yeah.
Yeah. And so basically part of an engineer's job is to make certain assumptions about like how do we model this problem that we're trying to solve, or how do we model this building that we're trying to build, or the bridge in this case that we're trying to build, and what assumptions can we make about it? And a very common assumption is that the material is pristine. In reality, and in modern engineering, that assumption is not made nearly as often.
That's good. Well, I guess it's one of those things. Like, that's what they teach you when you're learning, like, basic math, right? Like, oh,
Right.
assume a perfect sphere, but there's no such thing.
Exactly. And so the same thing is true. There's no such thing as a perfect material. And that's why a lot of times you'll see, like, if you have a sample, and the steel is a kind of an interesting example too, right? Because modern steels are actually extremely homogeneous. They're very, very well manufactured. There's very small amounts of imperfections in modern steel. But in 1845, or excuse me, 1828, when this was built, completely different story.
Right.
Steel was oftentimes full of imperfections because of the manufacturing process.
Yeah, you're eyeing it, too.
Yeah, and it's all kind of it's hand forged, right? These are all hand forged links to this chain.
Just smack it
So
with a hammer.
exactly. I mean, ultimately, it's not. It's a much more difficult process to control from an engineering standpoint. And so, obviously, the people at that time, they would have had no idea about the fracture mechanics and all that stuff. Um, so it's difficult to say what they could have done about it. But
Right.
anyway, so they kind of go through the report, and there's a couple reports that are made to the British government about it, and they decide, okay, the decision to widen the bridge was probably a bad decision. The bridge was never intended to carry that extra 6,000 pounds. We shouldn't have loaded it like that.
Yeah. That's just build a new bridge.
Exactly. And then the additional weight that was imposed by the width was actually all outside of the original trusses, basically, right? So if you think about like the suspension chains, they didn't like move those apart.
Oh,
They
the
just
center of gravity stayed the same?
the center.
Well, I
The
guess
center
they
of gravity,
changed it.
yes. Well, so if you think about like, they didn't change the center of gravity, right? But like, so the basically what I'm saying is the posts and the suspension chains, they remained like 14 feet apart. And then
they
they
just
just
added stuff
added
to the
they just
edge?
added on to the edges. So all that extra weight is only being held up by one of those chains, right, on either side. So you kind of have this compounding factor of like the extra weight only being carried by one set of chains, and it's the outside set of chains.
Oh, and you just never really... I mean, it's just things you don't think about until something like this happens.
Correct. So then it's thought that at the time, if the bridge had not been widened, it would have been able to accept the crowd loading of all the people. And in fact, there had been much larger crowds on the bridge, but people had been spread out more evenly across the two sides of the bridge so that all that loading wasn't put just on one side or the other.
Gosh.
So there's some more criticisms of like suspension bridge design that have been constructed. And there's some ideas then that basically, okay, maybe we shouldn't put suspension bridges in places where there's going to be like big crowds like this. Because at this point, there are a couple incidents like this where similar bridges have collapsed under crowd load. And then there's some more drive back towards like building truss bridges or more rigid structures. But finally, they decide that the primary cause of failure are these two eye bars that were defective. And this other guy, his name is James Rendall, who is another person who's on this commission to identify the problems of the bridge. He says basically any adequate testing would have discovered that these eye bars were not of sufficient quality.
Oh, so what he's saying is before you even leave the factory, just like attach it to 2 points and pull, and they
yank
probably
on it,
would have seen it.
Exactly.
Okay.
And so then what this actually leads to is kind of the institutionalization, I guess, of like regular, routine, scheduled inspection of bridges. And so the ICE, which is again the Institution of Civil Engineers, basically they recommend that all public bridges should be regularly inspected by a competent engineer in order to prevent this type of tragedy. And so that starts happening. So really, like, this is the initial failure that kind of leads towards regularly scheduled inspections of civil architecture.
Hey, you got to start somewhere. And it's wild. I know, like, we've gone on 14 different rabbit holes because engineering is that complex, right? Like, you start talking about material science, then you have to start talking about the physics of it. But this all started because folks were leaning over a bridge that was already modified, trying to see a clown in a bathtub powered by geese, even though the geese were alive.
Yeah.
It's just the happened circumstance of life is interesting, and engineering is just another language to sing that song.
It is. It's a beautiful, wild, crazy ride. But yeah, that's the Yarmouth Suspension Bridge.
Oh gosh, bridge failures are sad, but it's just crazy the things that cause them. It's not what you think. Like,
it's not. Yeah.
It's not what you think. Like a crowd, like a celebration. I didn't think about, like, last week, the marching in step, right? A crowd leaning over the edge this week. These small changes matter. And the fact that the history of the bridge is a big part of it, right? If that thing wasn't modified the way it was, or at least if it was modified with the proper precautions of, like, all right, let's reinforce it. Yeah.
Right. Yeah. And so, like, that's part of this too, is like, you got to think about it. Like, okay, how much should 300 people weigh?
It's a lot,
right?
It's a cool ton.
Assuming, yeah. So, like, let's assume, like, a lot of these people are kids.
Right.
So let's just say, like,
75 pounds?
Yeah. Like maybe an average weight of like 100 pounds person. So yeah. So it's 30,000 pounds. I mean, like, that's a significant load. Like, that's a lot of people.
And you were talking last week about, like, the bridge is only supposed to hold itself and what the assumed load is. 30,000 in carriage times is a lot on its own.
That's a lot of pounds.
On one side, forget about it.
Yeah. So, yeah. And I mean, bridges can certainly be designed to carry that load. And it had in previous circumstances, but not so isolated, right? And part of this, too, is as we move going forward, you start seeing designs in civil architecture and bridge building and stuff like this that are designed for worst case scenario, right? So it's like, okay, well, what if there were like 300 people that all crowded to one side of the bridge? What would happen, right? And that is because, like, these civil engineering projects are so expensive and potentially can lead to enormous loss of life that you have to start thinking about, okay, well, what happens if some idiot in a clown suit decides to go up the river in a bathtub with 4 geese?
Yeah.
And then,
it's
like,
the hypest thing that's ever happened.
Yeah, and then 300 people crowd to one side of the bridge. Right? So, like, and like, it sounds so absurd, but, like, that's so real at the same time of, like, it's just always these absurd things that then if you don't design for it, it's going to happen.
Right. Like, everyone expects, oh yeah, a boat's going to hit the bridge one day. No one expects several boats to hit the bridge at the same time. But the one summer that happens, you're in business.
Exactly. So it kind of shifts. It signals a little bit of a shift in attitude towards design and architecture that propagates through to today. Because we, in modern times, you see a lot of this redundant architecture and, like, high safety factors and design for, like, max use case scenario where you do have, like, crowd loading or resonance loading taken into effect and stuff like that. And then also, environmental factors, which I promise we will talk about next week.
See, I am paying attention. Like, in my head, I know, like, I'm also, like, an active participant of this podcast. I'm learning something every week, and I'm trying to put the story together, right?
Absolutely. So I won't give away, and I actually had, like, more content. I was going to talk a little bit about the Charpy impact test, but I think we'll save that for a future episode. Because I think it has a little bit more to do with a later failure that we'll talk about. So
sweet. I love Derek, that you have a backlog already.
Oh, I'm such a nerd that I'm already thinking, like, so far ahead.
Nice.
I'm so excited about it all. So next week, I won't give away the exact thing that we're talking about. But I will say that we're going to be going across the pond from England, in this case. We're going to be going across the channel into France. And we're going to talk about a French bridge that collapsed. And yeah, we'll get into that. So Derek, do you have anything to plug as we wrap up our episode?
You know, the normal stuff, nothing specific to me, but thank you for listening to another episode of Everything's a Spring by Jim and Derek Presents. Go ahead and follow us on our socials. We have an Instagram now. I haven't put much on it, we do have at Everything's a Spring, on Twitter at All Our Spring, because they didn't let us have all those letters. And of course, anywhere podcasts are listened to. I think we're pretty much posting everything regularly now. And I have one request of our gentle listener. If you're listening to this now when we were posted, or years later, you're going through our archive, if you know someone that loves engineering, knows someone that loves to learn, and knows someone that likes to listen to a couple dudes hang out, send them the podcast, because I have been greatly surprised by the types of groups that actually listen to this, even at episode 7. So, share the love. We'll be making episodes pretty much up until Christmas, I assume, right? And then we might take a breaker for a couple weeks. On one last note, I did buy myself, I got gifted some pretty nice scotch for the first time, which is a cool gift to receive. And I bought myself a fresh, brand new engraved whiskey grill because I really wanted one. I wanted a new one.
Awesome. I really appreciate the support, Derek.
Oh, it's a good product, man. I like good products.
All right. I love it. Well, Derek, let's bounce.
Let's bounce.